Okay, hi everyone. So today it's week 13. It's the final tutorial of the semester. Okay, and I know this period, I think most of you will be rushing your assignments and things like that. Same over here. Okay, but yeah, today we'll be talking about NP-Completeness. It's probably one of the biggest topics that is studied or in computer science. Okay, so yeah, let's just get to it. Okay. So quick administrative matters. Again, today is the last class and the official teaching feedback form is out. So I'll really appreciate if you can give feedback for my class this semester. Okay, you can either access it in Luminous, somewhere in the bottom right, you should see something like this, or via this website over here. Okay, so let's just quickly get to the table of contents. First, I'll talk about the different complexity classes. What's P, what's NP, what's NP hard, what's NP complete. Okay, then we'll talk about some basic questions regarding those complexity classes. And finally, we'll show a reduction, okay, by showing that we'll show that the CLIQUE problem is NP complete by a reduction from independent set and doing a bit more than that. Okay, so that's the plan for today. And let's just get to complexity classes. All right, so quick recap. So reductions, right? This is what I showed you last week. So A reduces to B, right? This notation is saying A has a polynomial time reduction to B. So it reduces from problem A. Remember, the direction is super important. So this is from problem A, okay? And you want to show these three properties. You want to show that after the transformation, if the input A was a yes instance, then input B is also a yes instance after your transformation, okay? And the other direction also applies, and the transformation takes polynomial time, okay? And these are the implications. These are some of the statements that imply. Okay, so if I have A reduces to B, okay, it means that if B has a polynomial time algorithm, then A also has a polynomial time algorithm. Okay, let's just focus on the third statement. So if A is hard, then B is also hard. Okay, more specifically, B is at least as hard as A. And I guess the way I like to remember it is I look at the sign of this inequality, right? So this oh, my pen isn't working. Okay, I look at the sign of this inequality and I look at, oh, B is greater than A, but greater than in terms of what, right? It's greater than in terms of hardness. Okay, B is at least as hard as, okay, greater than equals to. All right. So again, we discussed polynomial time with respect to the encoding of input, but this is just something to keep in mind. Not super duper important, but keep in mind regardless. Okay, so all right, so we'll learn about these complexity classes, but reductions allow us to kind of like group problems together, like which one is the one that's hard, which one is the one that's like easy in a sense. All right, so to build up our understanding about the hardness of problems, I'll use this kind of like number line. Okay, so left to right means that it's increasing in hardness. Okay, so this number line, I kind of took it from MIT notes. Okay, and I thought it was very helpful in giving me an intuition about the different hardness. Okay, people might draw it in terms of set, people might draw circles. Okay, I'll just draw a line and I'll show you in a bit. Okay, so P, what is P? P is the set of decision problems that can be solved in polynomial time. So we know that we have a polynomial time solution for them. Okay, so this is the set of decision problems that can be solved in polynomial time. So in terms of hardness, it's kind of like really the easiest as it can get. Okay, because we care about polynomial. We don't really care about like on squared, on cubed. It's the same group for us, right? It's polynomial time, right? So some examples are really the problems you have solved before, like shortest path, minimum spanning tree. This is things you have seen in the data structures and algorithms course. They have polynomial time solutions for them. All right, so this is P. So simple enough to warm up. So NP, right, is the set of decision problems whose yes instance. So if I give you a yes instance, it can be verified in polynomial time. Okay, note the slight subtle difference here. In P, we can start off from nothing and just solve it in polynomial time. In NP, what I tell you is that, hey, give me a yes instance. I'll tell you whether this thing can be verified in polynomial time or not. I use that yes instance to verify whether the answer is correct. Okay, so NP stands for non-deterministic polynomial. It's not non-polynomial, just fun fact, but the reason it's so, you don't really have to know. Okay, so NP is non-deterministic polynomial. But again, the intuition here is that someone will kind of like give you a proposed solution, and you want an algorithm that efficiently checks that proposed solution, which we also call a certificate, is correct or not. Okay, so the intuition here is that, you know, like when you do your past year papers, right? When you check your answer key, you verify, is the answer key correct or not? That's easier, right? Than coming up with the answer yourself, like during an exam. Okay, so this is really the intuition where someone gives you the answer already, then you just verify it in polynomial time. So these kind of problems that you can verify in polynomial time is in NP. Okay, so for examples, all problems in P are actually also in NP, which I'll talk about soon. But for example, like tree set and vertex cover, independent set, these are all problems in NP as well. Okay. For example, let's go through a concrete example, right? Partition is in NP. Remember the partition problem that we introduced last week? I give you a set of integers. Can the set be partitioned into sets of equal total sum? Okay, right? Can I divide it into 2 such that the total sum is equal? Okay, so here's the certificate, right? I give you, hey, I think this is the answer. Like I'll convince a verifier. I'll convince the verifier that this is indeed a yes instance by giving a proposed solution. I think this is an answer where I will return true. Okay, so what does the polytime verifier algorithm do? What it does is that it'll sum up both partitions, right? It'll sum up both the partitions and check that they are equal. Okay, so for example, you add them up, you see 32, you see 32. Yeah, but like, aha, great. So these two sets, right? These two sets that someone proposed to me is the answer is indeed equal, right? So, but are you convinced really that this means that this is a yes instance? Okay, so quickly just look at this. Like, seems to make sense. You sum up both sides and then call it a day that, oh yeah, they are really equal, right? But well, maybe the verifier should be a bit more careful. What it should do also is that check that the elements in the proposed solution also matches the input. So really ensure that everyone comes from the input. Okay. So I mean, the certificate could be something like 1-1, right? If the verifier algorithm, sorry, 1-1 and 2, for example, if the polytime verifier simply adds things up together, like 2 and 2 like that, then if it's convinced, then clearly this is not the answer to that, right? Because the elements don't really match. Okay, so showing that the problem is in NP, and take note of this because oftentimes you need to do this, okay, but typically it's the simplest step. Okay, to show the problem is NP, you should come up with a polynomially sized certificate format. Okay, so you should ask yourself, how does your proposed solution look like? Here in partition problem, the proposed solution looks like a set of 2 numbers. Okay, and then you should design the polytime algorithm that verifies that certificate. How do you confirm that the answer is not bluffing you in a sense? Okay, so maybe I just want to quickly check, is everything okay? Like, do you guys have any questions about what P is, what NP is? Okay, so give me a thumbs up if it's okay, and all right, and do ask if it's not, right? All right, great. So a couple of thumbs up. So okay, so what we know, right, is that P, all problems in P are also in NP. Okay, in other words, P is a subset of NP. Okay, how do you like prove this, right? Like a proof sketch. So if a problem is in P, right, and you're given a proposed solution, remember you want to verify this in polynomial time. How do you check it? Okay, well, because problems in P means that we can solve it in polynomial time already. Okay, what we can do is just completely forget about the proposed solution, just run the polynomial time solution to the problem in P, and then return that yes or no answer. Okay, because if we are given a yes instance, right, means that there should exist a solution, right? And the polynomial time solution can tell us that, like, hey, I have a solution for you, right? Without even checking what the proposed solution is. Okay, thus every problem in P is also in NP by this argument. Okay, so this is the rough argument for why all problems in P is also in NP. All right, so now we'll switch gears. Okay, from P and NP, we'll start talking about NP hard and NP complete. So NP hard is the set of decision problems that are at least as hard as the hardest problem in NP. So I mean, remember this diagram over here, and I have kind of gives you like a measure of the hardness, right? The hardest problem in NP is like right smack at the end here. NP hard says that if the decision problems, they are at least as hard as this guy over here, as the hardest problem in NP. Okay, so well, you might be thinking like, how do I know if a problem is in X is NP hard, or how do I know like if the problem is the hardest in NP? Let's stay tuned for that in a bit. Okay, I'll talk about that very soon. So this is NP hard, at least as hard as the hardest problem in NP. So you can visualize it this way. Okay, now NP complete, right, is the set of decision problems that are satisfy two conditions. First, it is NP hard, in NP hard, okay, and at the same time, it is in NP, right? So you can think of it as is the intersection of NP and NP hard. So it's right smack in the middle here where it overlaps, okay? So an alternative perspective is that if a particular problem is in NP, right? NP complete means that for all problem A in NP, A reduces to X. Okay, so every problem in here, right? Every problem here will reduce to NP complete problems. That's another alternative way to think about this, and I think this was the one introduced in lecture. I can't remember. Okay, but if it's difficult for you to imagine this alternative, just take it as problems in NP and problems in NP hard. The intersection is the NP complete. Okay, so intuitively, this is exactly what I mean by saying that they are the hardest problems in NP, right? Because NP hard is here onwards, and the only time it intersects is at the tail end of the NP class. So this is NP complete. Okay. So before that, definitions wise, is it clear? Okay. So again, thumbs up if it's okay, because these are really like definition spam. Okay, but I want you to be clear on what the definitions are, and if you aren't, ask me now. Okay. I'll keep this number line like throughout the slides. So if don't worry about like forgetting them. Okay. So now, just now I said that NP hard is the set of decision problems that are at least as hard as the hardest problem in NP. So how do I know if a problem X is NP hard? Like I want to know, like I have a problem X here. Does it fall in NP hard, or does it fall like somewhere else or something? Or I'm just interested that it falls in NP hard. So what I do is that I take any problem A that is known to be NP complete, right? Just take somebody here, A that is in NP complete, then show a reduction from A to X. Okay, show that a reduction exists from A to X. And because this notation here, right, as I said, intuitively it says that X is at least as hard as A, right? That is exactly what it means to be NP hard, right? Because the hardest problem in NP is exactly A over here, which is NP complete. You do a reduction to X, right? And it becomes at least as hard as the hardest problem in NP. So this is how you want to show that a problem X is NP hard. Okay, you keep this in mind because you have to do this during the exam. I think you have to do this during the exam or even in your assignments. Okay. Again, as I said, this is where it's very, very important that you get the reduction right, the direction right. Okay, to show a problem is hard, you need to reduce from A, right? You must not show that X reduces to A. This is not correct. Okay, you want to show X, you want to show that X is NP hard, you should start from a already known hard problem, then reduce it to X. Okay, you cannot do it the other way around. It's just not doing the right thing. Okay. All right. So now that's all the definitions. I think that's out of the way. And I think the very famous problem that I believe like a lot of computer science students must have heard about is the P versus NP problem, right? Because here I've argued that P is a subset of NP, right? The biggest unanswered question right now is that is P actually equals to NP? right? Are they actually the same class of problems? We don't actually have an answer yet. Okay. Alternatively, it's kind of like asking like, hey, is there somebody that is not in P, but it is in NP? Right? That's an alternate way to think about this problem. And I think just a quick story time, I think many computer scientists believe that P is not equals to NP, right? And there's this whole quote, but I think like one way you can think about what this quote is saying is that, because remember, P is about having the solution, right? And NP is about verifying the solution. So it's kind of like, if P equals to NP, it's kind of like if you try to verify something, it has the same difficulty as coming up with it. Okay, so suddenly what this quote is saying is that maybe you'll be as smart as Prof. Warwick, for example, because the way he thinks, right, it's kind of like equivalent to how you verify what he thinks. Okay, so here, like in particular, it says here, no fundamental gap between solving the problem and recognizing the solution. Okay, so this is a particular quote why some people believe that P is not equals to NP. Okay, of course, no one has proven it yet. Okay, but it's a I think the consensus typically believes that P is not equals NP, with a couple of people thinking it's equal. All right, so that's the P versus NP problem. And maybe I'll just quickly mention that NP-complete, surprisingly, there are many problems known to be NP-complete. So you see that this intersection over here, right? But as it turns out, this intersection actually has a lot of things. Okay, you might have seen in lecture the tree-set problem, the independent set, vertex cover, they are all NP-complete. Right? So the interesting thing over here is that if we know a polynomial solution to just one of them, right? It doesn't matter which one. If you know one of them has a polynomial solution, suddenly every single one of them, we have an efficient solution for it. And because NP-complete problems are reducible to each other, okay, or at least there's a chain of reductions that we can do. But right now, the problem is like we don't really have an efficient solution. We don't know. Okay, we won't say that we don't actually have, but I'll just say that we don't know that whether it exists or not. Okay, so this is the NP-complete. Maybe you might be thinking like, hey, why should you care? You know, because seems very theoretical. So interestingly, I was talking to some of my friend and senior last time at work, right? They actually have actually like dealt with problems related to NP-completeness before. Like there's my senior here in Ninja Van. Apparently, like he worked on an NP-complete problem related to traveling salesman. Okay, and my friend in Shopee was in the tech ops team. I think he did something like scheduler that is NP-complete or something. Okay, so I guess if in case one day your boss gives you a problem, if you somehow show a reduction and prove it's NP-complete, you can tell your boss, hey boss, you know, this problem is actually super duper hard. No computer scientist has come up with efficient solution for this. Okay, so maybe this is why you should care about P versus NP. Okay, and this whole study. All right, so all right, so that's just very quickly the overview of the complexity classes P versus NP. So I want to check like any questions so far. Okay, I think that was rather fast in terms of I just give you definition after definition, but I'll open the floor for questions if any. Please give me a thumbs up if it's okay though. Okay. All right, so a couple of thumbs up. Thank you very much. So let's go through the tutorial question now. Okay, so the first question is there are some of these statements, right? So, well, maybe you don't want to prove P equals to NP directly, but some of these statements, right? It's going to imply P equals to NP. Okay, which one of it do you think it is? Okay, so if I know probably in P there is also NP-complete, or is it like probably in P there is also an NP, or there's a problem in P there is also NP-hard? So which one do you think it is? Try thinking about it and fill in archipelago. Okay. So let's resume it. Okay, let's not spend too long because I'm worried about the final question about the reduction. Okay, let's resume at 11:23. Okay. Actually, a lot of answers are coming in already. You might want to check question 2 as well if you like. Take note, I think question 2 was intended to be multiple response, but I forgot to set it to multiple response on Archipelago. Okay, so let's resume. Okay, so these statements, which of the following imply P equals to NP? Okay, most of you got it right with a couple of mistakes here and there. That's fine. So the first option is true. Okay, so there's a problem in P that is also NP complete. So, but intuitively, how do you get to this answer? Like the way I thought about it is I look at this number line, right? If there's a problem in P that is also NP complete, it means that intuitively the set P kind of like covers this entire thing. Like it reaches all the way to NP complete. So you can see visually now P is equals to NP. If this is such that it happens, there's a problem in P that is also NP complete. Well, now the entire thing, the set P equals to NP. But let's try to formally argue about it, right? Because you don't want to like draw a number line and argue like that in the exam. Okay. In particular, last week I showed this, where if I reduce from A to B, right? One of the statements says that if B has a polynomial time algorithm, then so does A. So if this guy has polytime, it implies that A also has polytime. Okay, we'll focus on this particular statement in order to prove what we want to do. So formally, right? Formally. Now, a problem in P is also NP-complete. Remember that NP-complete problems, right? They are all NP-hard problems. They are all NP-hard problems, right? It means that one of them is now solvable in polynomial time because of the fact that we assume now a problem in P is also NP-complete. So it's also solvable in polynomial time. So a particular NP-complete problem, right, which is actually like also NP-hard, it's also solvable in polynomial time. Okay, so remember that by definition, what it means to be NP-hard, a problem is NP-hard if you have a reduction from all the problems in NP. So every guy here in NP has a reduction to an NP-hard problem, to that NP-hard problem. Okay. So by definition, this is the second statement is by definition. All right. So what does it mean that now a particular NP-hard problem, right? A particular NP-hard problem, like in particular this guy, has a polynomial time solution. So it's a polynomial time solution. It means that by this statement over here, if the NP-hard problem is solvable in polytime, that means all the problems in NP is also solvable in polytime. Okay, I'll say that again. First of all, we assume that there's a problem in P that is also NP-complete. So that particular problem, which also happens to be NP-hard by definition of NP-complete, is now solvable in polynomial time. Okay, so we remember the definition of what it means to be NP-hard. NP-hard means that all the problems in NP reduces to that NP-hard problem. Okay, but that exact NP-hard problem, which we have a polynomial time solution for, right? Because we reduce to it, it implies that the all NP, which we reduce from, also has a polynomial time solution. Okay, and if the last statement is confusing, it's actually just copy pasting this exact statement over here. Just piece things together. What is B? What is A? So now all the NP problems are solvable in polynomial time, and this is what it means. This is what it means to be in P. All the NP problems are now solvable in polynomial time. That is exactly what the definition of P is. Okay, so this is problem 1. Okay, this is implies P equals to NP by definition of P. Okay, so this is question 1. Any questions about this option? If not, I know this might be confusing, but again, just keep the intuitive view that the set P now completely reaches NP. Okay, so option 2 is false. It's saying that there is a problem in P that is also in NP. This is like by default already true in the first place, right? So we have earlier argued that P is a subset of NP. So this does not imply anything about P equals to NP. So there's nothing, like right now the status is still unknown, so it doesn't help us in proving. And the third option is that there's a problem in NP that is also NP hard. This is exactly what it means to be NP complete. Okay, so we already have NP complete problems, so we don't know anything new about P equals to NP. Okay, so these are the 3 options for the first question. All right. If you have any questions, again, PM me, right? But I'll just go on. So the second problem is asking like this. I have an NP problem. One day, someone proves that this problem in NP, like one of this problem in NP, we cannot solve it in polynomial time. So impossible to find in polynomial time. So now, which following classes are now known to be not solvable in polynomial time? Okay, so first of all, like the polynomial time is in NP. Sorry, the problem is in NP. Suddenly, someone proved that hey, if there's no way this has a polynomial time solution. So which one of these problems? Sorry, this 1, 2, 3 among the 1, 2, 3. Which one of it we don't have a polynomial time solution for after this discovery? Okay, so give it a quick thought. No need to fill in archipelago. I think archipelago, I wrongly set it up. Okay, it's a multiple response. Okay. So I'll resume at 11:30. But first of all, any questions about the question? Like, is the question confusing? Okay. All right. So let me just quickly check archipelago in case you answered it there. Okay, no one chose the wrong option. That's great. Okay. All right. So again, this is the notion that we'll use. I say that A reduces to B. It means that if A is hard, then so is B. This is the thing that I will use for this question. Okay. So intuitively, right? Like if I say the problem in NP is not solvable in polynomial time, whatever is harder than, like whatever is to the right, whatever is harder, now also cannot have a polynomial time solution, right? If the easier problem cannot even solve it in polynomial time, what hope do we have for the harder class of problems? Intuitively, that's how you might think about this problem. So again, all NP hard problems, right? This is true that now we don't have a polynomial time solution for them. The reason is because L is now hard, right? And L reduces to NP hard problems. That means NP hard problems are also hard by this notion of like one of these statements. If A is hard, then so is B. Okay, so L is now hard. And because L reduces to NP hard problems, that means NP hard problems are also hard. Okay, so this is very brief, but this is really all there is to it. Okay, option 2 is false, right? Because, well, we already know that P can be solved in poly time. It's a set of decision problems that can be solved in polynomial time, right? So it doesn't say anything about, you know, like now the entire NP cannot be solved in polynomial time because this P is indeed solvable in polynomial time. So option 2 is false. Option 3 is really the same argument, right? Because the fact that NP complete problems are NP hard and in NP. So there's really nothing different in the argument from compared to the first option. Okay, so this is question 2. Okay, if you have any questions, do PM me again. I think this question might be easier to grasp compared to the first one. Okay, but I'll just go on to, first of all, before we go to question 3, I want to like complete the argument. Like, how do I show that a problem is NP-complete? Okay, recall, NP-complete means it's both in NP and NP-hard. Okay, and the steps are actually very routine. Like, it's following the same steps every time, but the thing is they are just not easy to do for different questions. Okay, so again, as I said, it's both in NP and NP-hard. First of all, we want to show that X is in NP, right? Because I want to show part 1, I want to show it's in NP. How do you do that? You propose the way how the solution looks like, the certificate format. How does the proposed solution look like? And then you tell me an algorithm to verify the certificate. Okay, how do you check if the proposed solution is legal? Okay, this is step 1, show that the problem is in NP. Okay, the second step is to show that it's NP-hard. How do you do that? I've mentioned this earlier. You take a problem known to be NP-complete. You take a problem known that fits right here already. Okay, then you show that you can reduce from A to that problem X, Reduce it from A, then go to X. And maybe it's worth reminding you, what's a reduction? Reduction is a transformation. Okay, so when you reduce from A to X, you transform the input of A into an input of X. Okay, so this is what how to show that problem is NP-hard, and you prove these statements to show that your reduction is correct. So meaning if you start off with a yes instance, it stays as a yes instance, and vice versa. Okay, and show that polynomial time, it takes polynomial time. And again, direction is super important. This is why I keep reminding you. Please don't get the direction wrong. Minimally in the exam, get the direction right. It's okay if you cannot come up with the reduction, but please at least get the direction right. Okay. I might mention that it doesn't matter which order you show it, right? As long as you show both of them. Okay, so this is how to show a problem is NP-complete. Now, third question is to show. Okay, so I'll introduce the two problems. Independent set. I hope you have seen this in assignments before. What an independent set is. Basically, you want a subset of vertices such that in the original graph, they don't have an edge. So like for example here, if I take a subset of them and they have a edge between them, this is not an independent set. Okay, but the problem of here, the decision problem is to ask like, hey, does this graph have an independent set of size at least k, right? So I'm satisfied as long as like I can have an independent set of size at least k. So for example, if k is 2 over here, I'm satisfied with this. This graph is a yes instance, right? Because this graph together with k equals to 2 is a yes instance because we have an independent set of size 3, right? It's at least size 2. And I should mention that the input to this problem is a graph and the number k. Okay, graph and the number k. This independent set. The CLIQUE problem. Okay, CLIQUE is asking a set of vertices U of graph G is a clique if every pair of vertices in U has an edge in G. And intuitively, what this means is that a subgraph of G is a complete graph. So like for example here, if I ask, given this graph and k equals to 4, right? Is there a subset of vertices? Is there a subset of vertices that forms a complete graph of at least size 4? Right? The graph is at least size 4. Oops. So there is over here in this graph. Okay. So this is the CLIQUE problem. And we want to show that the CLIQUE problem is NP-complete. Okay, and well, the hint kind of I put here is try a reduction from independent set. Otherwise, why did we introduce it, right? So is the problem statement clear? Okay, so I hope the problem statement is clear. Okay, I won't ask archipelago because I'll just go on. It might take some time. Okay, so one thing to note about reductions is that I think coming up with a reduction is an art. Okay, you might not always succeed the first try. So for this tutorial, what I try to do is to build up some thought processes, how to come up with the answer. Okay, which I think is very lacking in a lot of like solution write-up out there. They just like whack hey, here's the reduction, here's the answer, without any intuition on how you got to that answer. Okay, so I'll try to build it up. Okay, I want to, first of all, just a quick check. I want to show that CLIQUE is NP-complete. We'll do a reduction from independent set. So does this mean that we are going to design an input for independent set or design an input for the CLIQUE problem? Okay, quickly PM me which one do you think it is? Design for CLIQUE or design for independent set? Because we are coming out with reduction, right? Okay, so we transform the input from something to something. Okay. All right, so I've got a couple of answers, and indeed it is to design an input for the CLIQUE problem. Okay, start off from independent set and design it for the CLIQUE. Okay, so recall the pseudocode, how it kind of looks like. So you start off independent set, have an input G and K, and then you do a reduction, and then get G prime and K prime. Okay, and this CLIQUE problem, we have a magical solver for it. And I want to make a note that G prime and K prime may or may not be the same as the original input. Remember, you're allowed to tweak it. You're allowed to tweak it. Okay, so we want to show for a correct reduction, it means that if one of them is a yes instance, then the transformed version is also a yes instance and vice versa. Okay, this is what we want to show for today. Okay, so now let's start building up the idea for the reduction. So let's say I have this graph over here as the input to the independent set problem with K equals to 4. Okay, so the first thing I tried, so last time when we came out with this tutorial question, okay, I tried doing it myself. So this is what you see today is really my thought processes. So the first thing I asked myself is that, should I modify this graph to the input for the CLIQUE, right? Can I give it as is? Or maybe should we modify K? Is K maybe like, instead of 4 in the CLIQUE problem, do I give it 5 or does it stay as 4? Okay, so that's my thought processes. Okay, then I noticed, I was thinking, you know what? We wanted to prove that if this was a yes, it's to independent set, I abbreviate to IS. Okay, we want it to stay as a yes instance to CLIQUE. Okay, so I was thinking, okay, let's suppose this is actually the yes instance. Okay, indeed, this is the yes instance, like I designed it as such. It's a yes instance to the independent set because I have an independent set of size 4. Right? I quickly noticed one thing. The independent set means that I have no edges between them in the original graph. This is by definition of independent set, right? This subset of vertices, they do not have edge between them by definition of independent set. Then I look at it, I think of the CLIQUE problem. Hey, the CLIQUE problem is kind of like the total opposite, isn't it? Right? If I want a size 4 CLIQUE, it's kind of like I should add edges everywhere now. This is totally empty. The CLIQUE problem is total opposite. I need to completely add edges everywhere for the CLIQUE problem. So a yes instance to a CLIQUE problem might look like this. I add edges everywhere. Take note, at this point, I haven't told you how to exactly modify. But the idea that I came up with is that, should I somehow modify the graph to add edges to form a CLIQUE of size 4? Right? So does this thought process make sense? Can I get like a thumbs up if it's okay? If you want me to repeat something, please let me know. Okay. Okay, great. Yeah. So now this is kind of like a starting point, right? So you might be thinking, okay, so how exactly should we modify, right? So one thing we note is that we can deduce that the integer K doesn't change, right? Because both IS and CLIQUE takes in a graph and the K. But one thing you notice just now from this observation is that probably K doesn't need to change. It stays as 4. Okay. But the thing is, right, we should also somehow add all edges to the independent set to form a CLIQUE, right? Because this is exactly what we did. From empty to everywhere has edges. How do we exactly do it? So I know I thought of some attempts. Okay. So maybe the first attempt, right, the very trivial attempt is that you don't know where to add the edges. Just add edges to the entire graph. Just add edges to the entire graph. Okay, so my reduction that I propose, right, the first attempt is that K doesn't change, but I modify the graph such that I add edges everywhere and the CLIQUE problem becomes a complete graph. Okay, so, so does this work or not? So let's think about it. one of the conditions for the reduction to be correct is that input to the clique is a yes instance, implies that the input to independent set is also a yes instance. This is the reverse direction. Okay, so the problem with the current approach is that when you add edges everywhere, right, by default, it will always, no matter what, it will always become a clique, right? It'll always become a clique, regardless of the initial graph. That means that if the input to the original problem, it is originally a no instance, suddenly it becomes a yes instance for the graph. Yeah, okay, so I've got a proposal. Why not inverse the edges? You're jumping the gun, kind of. Yeah, that's the answer. But yes, well, inverse the edges in a sense will be the answer there. But here I'm trying to like build up ideas, you know, and show like why they're incorrect. Okay, so that's fine. Like you don't have to apologize. That's a perfectly valid idea. Okay, so well, this is the problem with this approach. Okay, so attempt 2, right? Like I'm showing like why this another attempt which also doesn't work. Okay, maybe if you think about it, we are adding too many edges, right? Now it becomes clique everywhere. So notice how we only needed to edge the vertices involved in the independent set. If that's sufficient, right? So just add the edges here. We don't need to edge. We don't need to add it over here. Okay. So well, my reduction attempt number 2 is that, you know what? First of all, let me find which one of it is involved in independent set. Okay. And then I notice 4 of these edges, vertices are involved in the independent set. So let me just add edges to those vertices. Just add it there. Don't need to add over here. Okay. So is there a problem with this? Well, I mean, it's still an attempt, so clearly there is a problem. Okay. Which the first one is that we want our reduction to run in polynomial time. Notice that finding that relevant vertices is itself the NP-complete independent set problem. So remember, we want to make use of the clique problem. We want to rely on the clique problem to do the hard work for us. But yet, the reduction attempt here is saying that, you know what? First of all, solve the independent set problem and then add edges there. It's kind of like very wasted work. Okay, and you might think this is silly. Okay, but I'll tell you that in my semester, the assignment we were given, like a lot of people were thinking about doing that, something like that, to solve the problem, to do the reduction from the problem, solve the problem itself, which is incorrect, right? Because we want a reduction to run in polynomial time, and we don't know the polynomial time solution to do that. And second of all, the problem is that we can still form yes instances to clique from a no instance of an independent set. Okay, so for example, over here, I want an independent set. This is a no instance for IS, but this is a yes instance for clique. Like, so this is some problems I laid out for this reduction attempt. Okay, so you know, like some of you who are fast, like for example, the one who PM me might think like, you know what, this is all like, why am I going through all this? I think I just really want to show examples where reductions fail, right? And we try to fix it along the way. Okay. So some lessons from the previous attempt is that you notice that aside from adding edges, we might need to remove some edges, right? Because if you add, for example, from the first one, if you add too much, we want it such that we remove some so that no instance stays as a no instance in a sense. Okay, and we also need to do the reductions without any information about the existence of the independent set. This is trying to say that you don't solve for independent set. Just do the reduction without anything you know about whether there's an independent set or not. Okay, so which brings us to the actual correct reduction, which one of you have proposed to me, is to take the complement graph. Okay, so the formal term for it is the complement graph, and intuitively, what it means is that if two nodes they origin have an edge, remove them. So like you see this edge over here, now it's missing, right? Then this edge over here, now originally it was missing. So that's the complement graph. Okay, that's the complement graph. And the K remains the same. I set K prime equals to K. Okay, so hope this reduction is clear, but I'll argue that it's indeed correct. Okay, but if you have questions, do PM me, like what the actual reduction is to take the complement graph. So now let's argue that if input to IS is a yes instance, it stays as a yes instance in CLIQUE. How? Okay, so Okay, so I'll read it off one by one. So read it point by point. So I consider the independent set size at least K and G, right? So this is at least 4. Is 4. Notice how by the definition of independent set, none of the nodes share an edge, right? Because the reduction, now transform it to the complement. Now every of these pairs have an edge between them. Because of that, now we have a clique. Now we have a clique that is also of size at least K. That means that this new input that we design for the clique problem is also a yes instance. Okay, so is this argument clear? Can I get a thumbs up if it's okay? It's kind of like formally arguing whatever I talked about like earlier from the intuition. Okay, so great. So I see a couple of thumbs up. So the other direction, fortunately for us, is actually exactly the same argument. I don't think I'll repeat it. It's exactly the same argument as before, just that you start from the clique. Now you consider that originally it was flipped, right? In the clique problem, in the original problem that you give to the independent set, there were no edges at all between them. So I think I won't spend too much time here. Think about it, it's actually exactly the same argument, just in the other direction. But I want to mention that generally not all reductions will have identical arguments in both directions. It just so happened that this is between two graph problems. They are very easy to argue, right? To have the same argument. For example, revisit the tutorial example from before. Partition to knapsack don't have an identical argument between them. Okay, so this is what I'll mention. And finally, reduction runs in polynomial time with respect to the input, because all we do is to complement the graph. In particular, it just takes time O of the size of the vertices, right? Of size of vertices squared, because complete graph is V squared. And complement, if you think about it, if you put together, if you overlay the two graphs together, they'll form a complete graph, which has V squared, O V squared edges. Okay, so it takes polynomial time. So what have we shown? Did we show that CLIQUE is NP-complete? Right? Can I get a yes or no for this? If it's a yes, then I guess it's a yes. If it's no, what do you think is missing? No one's saying anything. Yes, exactly. So one of you have said no, because all we have done is that to show that CLIQUE is NP hard. We haven't actually shown that CLIQUE is in NP. So I made this meme over here because typically, don't forget to show that X is also in NP. Okay, so these are the two steps. All right. So showing the CLIQUE is NP, fortunately, isn't that difficult. All you need to do is a certificate, right? Propose solution. You propose that, hey, here, I think this is the answer. You give me the set of vertices, right? Then the verifier, all it checks is two things, right? First of all, it checks that the size C is greater than or equals to K, because this is what we want, right? We want the clique size to be at least K, and we verify that every pair of nodes has an edge in G. It actually forms a clique. The second step is to actually show that it forms a clique. All of this can be done in polynomial time. Okay, so therefore, CLIQUE is also in NP. So in a sense, this is easier to do, but I chose to do the NP hard first, just so that to remind you, like, hey, don't forget about this easy step. Okay, this easy step, just do it first. Okay, so as a summary, that really is the end of the question. Showing that the problem is NP-complete, really, you have to show two things. First, show that it's in NP, and second of all, show that it's NP hard by doing the reduction. Typically, showing that X is NP hard is the harder thing to do, right? It's the less trivial things to do, and a lot of people might find it more difficult. Okay, so this is how to show a problem is NP-complete. And maybe just give this a quick read. Like, what is wrong with this argument? Like, I saw this image online somewhere, okay, and I thought, hey, you know what? This doesn't make any sense. What do you think? Okay. Okay, I think I don't have too much time, but I'll just mention that the problem here is that they say that among us, okay, is NP-complete by giving a reduction to set. Okay, so but the thing is the direction of the reduction is important. So by right, what the correct things they should say is that if they give a reduction from the satisfiability problem. Okay, so okay, I think the final part I can mention later. Let's see. Okay, actually, I'll just mention it now because, you know, NP-complete problems, we don't have an efficient solution for them, right? So what can we do? So fortunately for us, there are different things we can do. So randomization, for example, allows us to have better algorithms with some error perhaps, or maybe we leverage on special cases. One of the assignment questions is to do, I think, greedy algorithm to do max independent set on trees. So this is a special case. Or there's this thing called approximation algorithms that kind of like give approximately the correct answer. It's not too far from the best answer, but it's close enough. Okay, so with that concludes pretty much the tutorial. If you want some additional resources, here is some things that I can recommend. Okay, there is a reduction from tree set to Super Mario Brothers. Like you might think, huh, Super Mario Brothers, but do check out the video. I think it's very interesting. Okay, and if you want to use the textbook, I personally recommend this other textbook, which I think Prof didn't mention, because I think the CLRS textbook, the material, it might be a bit too dense with respect to 3230. So I personally recommend this book for this chapter. Okay, so that's it. Congratulations. This is the end of tutorial for 3230. Okay, give yourself a pat in the back. A lot of difficult material, really. And so just a quick mention, revision for finals. Recording can be easily found if you go to module overview and click on these like weeks. Okay, I've set it up so that you can find the recordings easily. I'll release past finals and practice sets soon, but I recommend that you follow whatever resource Prof Varut releases, because the assignments he set and the questions he released are more closely related to whatever he might say in finals, I personally feel, because different semesters have different professors. Okay, so before we conclude, like, because it's our last class, let's take a class photo perhaps. Okay, so I'll pause the recording. So, and if you're shy, that's fine. Okay, so okay, so that is the end. So I'll share the slides in the Zoom chat and maybe the link to the feedback, but I'll also quickly mention about going forward, like after 3230, like what's there, right? So if you're interested, you can talk to me about it. Okay, so this is the slides and feedback for the semester. But yeah, it's been really fun. I always enjoy teaching the module. I hope I made it easier or at least bearable, because I think 3230 is a pretty hard module. Okay, so I try my best to give intuitions and here and there so that it's more manageable. But going forward, what 3230 unlocks, right? Next semester, if you're interested, you can take optimization problems, right? So this is, we study NP hard problems, right? So how do we do better? Or how do we do as best as we can? Give approximate answers. Okay, or if you're interested, there's this module called algorithms at scale. How do you deal with super large data? Right, this is what algorithms at scale is about. Okay, maybe you want to do like efficiency if you don't have enough storage, for example. Okay, this semester, which is the current semester, right? But if you're interested in the future, you still have time, you might consider parallel and distributed algorithms, right? Where we design algorithms in, it's pretty self-explanatory, parallel and distributed setting. Or if you're interested in randomized algorithms, there's a whole module dedicated to randomized algorithms, which I'm taking now. Okay, so so these are some modules related to algorithm and theory focus area. I think 4261 mechanism design is Prof Varut's module, right, where he relates algorithms and game theory. Okay, and yeah, I'll just keep this slide as it is. I won't mention too much. Okay, but if you're interested, you can talk to me about it. Even if I haven't taken it, I think I should know some people who have taken the module before. Okay, so that's it. Thank you very much. I quick mention. Okay, so I've come up with extra questions. So if you want to practice, you can try to come up poly time reduction from 3 set to 4 set. Okay, or the other way around, 4 set to 3 set. Both reductions actually work. I worked it out with a student this semester, and we came up with like 2 different solutions for both of them. Okay, my slides, they have extra things that were based on previous semester's question. Okay, so this is one of them. There's another one that is actually a super difficult reduction from 3-set to Hamiltonian cycle. So I keep it as it is because if you're interested, but the reduction is super complicated, as you can see over here. We omitted it from the tutorial this semester, but if you like to study it, I keep the slides over here, and I have a recording still for it. I actually linked it somewhere here. Yeah, so I linked the recording over here. Okay, so final conclusion, if my materials all can be found, if you click the link over here, okay, everything is over here for your revision needs. I will hold consultation over the reading week. If you need help or if you need to schedule one-on-one, you can PM me directly. So I think that really concludes what I want to say for this semester. This is my last tutorial for you guys for this slot. Okay, so thanks a lot. It's been really fun for me. Hope that it's really fun for you as well. Yeah, you're welcome. Okay. So, yep, class is dismissed. If you have to go, please please go. And if you have things to ask to me, sure, I'll stay back for questions. Okay. No problem, no problem. Oh, I see that someone reconnected. Do you have something you want to ask? Okay, so I have a question. Okay, so let me just share screen. I'll just say what you think is the reduction. Okay, so the question is, for 3-set to 4-set, is it cheating if you do x1 or x2 or x3, then you become this? So for the context of okay, so I'll mention that I think how Prof. Varut introduces 3-set and 4-set, this is not cheating because he doesn't necessarily need you to have distinct literals for the clause. So this is legal for what Prof. Varut introduces. In the previous semester, I was taught that the clause needs to be distinct. Okay, so I will say that this is not cheating for the purpose of whatever Prof. Varut has taught you. Okay, I think so. Let me quickly check. Lecture 10, I believe. Preset. Okay. Wait a minute. Corresponding to different literals, different variables. Did he change it? Because I thought he kept it as. Yeah, okay. So yeah, in lecture 11 slides, he said not necessarily distinct. So it's fine. Okay. But let's see whether this works, right? So let's think about this. So what do you think? Like why do you come up with this? We can discuss, that's fine. I'm happy to discuss it now even.
Nothing in particular. It was just a random thought. Because let's say you always take the first literal in every clause.
Yep.
This is a clause, right? Like x1 or x3.
Yeah, the entire thing is a clause. Yes.
Yeah, I was thinking if you always take, let's say like maybe the first literal in every clause, then you just throw it back again. You should always get back the same assignment. Not really. Yeah.
Okay.
So like basically the last literal is always useless and therefore show only.
I see. Yeah, actually, now I think about it, this so I guess this is the third solution. So let's argue it carefully, right? So 3-set, yes. implies that for set is a yes instance, because that means that if the tree set instance is a satisfied instance, that means it's this is satisfied. So it means that this one will also be satisfied, right? Because it only cares about this guy over here, right? Because one of these things must be satisfied, so the entire clause is indeed satisfied. So this is okay. But what about for set yes implies that tree set yes? Okay, so that means if I have this instance, if this is satisfied, that means one of these things, one of x1, x2, or x3 is true, right? Basically, for with respect to that clause, that means by default the tree set instance is also a yes instance. Yeah, I think this works. This is way simpler because we allow not necessarily distinct, right? So I think this is a fine reduction. I think this is a fine reduction if we allow duplicates in the clause. Okay, so I guess if you like extra challenge, think about it when it's distinct literals in the clauses. Okay, or maybe you can also try the other direction, for set to tree set. I think this is more non-trivial. So
for the hint, yep. I just saw the hint. You want to introduce additional new variable.
Yeah.
So if we introduce a new variable, then we keep it as the default variable, and then this final variable, let it be like xk, right?
Let's call it z. Yeah, z to be right.
Yeah, let z always be false. Then
no. Right. So this is the tricky part. So I think this is good to mention here. So for tree set to for set, this is fine. This is perfectly fine. We set it to false, right? We set if any one of this is true, this one is going to be true, and it doesn't matter what z is. Correct? That's the argument for
yes.
For set. But for set to set, the argument here is tricky because it means that there exists a solution for this thing, right? There exists a solution for this thing. You cannot, based on this alone, you cannot say that the yes instance is because z is false. You cannot say that z is definitely false because all you know is that the for set solver will tell you, hey, there is a yes, this is a yes instance, right? But it doesn't tell you how exactly each one of this is assigned. You don't have a control over how you assign these values. Okay, so you cannot say that z has to be false. Do you get what I'm trying to say here?
Then in that case, doesn't the previous one not hold as well? Because there could be a case where I don't duplicate the first variable, right, in the for set.
So you mean your first reduction, is it?
Yeah, the first reduction. So going from for set to tree set for the first reduction.
No, that
I also cannot.
Okay.
Sorry.
Okay. So all right. Sorry to interrupt. So sorry, you finish first. Yeah.
Yeah. I also don't have control over the last one, right? For the first reduction.
You're right. You don't have control over the last one, right? So okay, let's carefully make the distinction what's going on. So for your first case, right, you don't have control over the last one, but take note the last one is identical to x1. So meaning that in the for set yes to the tree set yes, one of the following must hold. It must be that, okay, this is too long, so x2 false, x3 false, right? Okay, so the thing we know is that the for set instance, this for set instance, let's say it's a yes instance. It means that one of this thing must be true, right? We don't know which one, x1, x2, or x3. Or the final x1 again. We don't have control over the last one, but we know that at least one of them is true. Okay? We know at least one of them is true. So therefore, the tree set instance has to be satisfied as well because one of x1, x2, or x3 is true. Okay? The subtle difference with if you introduce a new variable z, okay, is that again the same thing. One of this thing, so I want to argue that for set yes implies that tree set yes. Okay? I know that one of x1, x2, x3, or z must be true, right? Because that is what it means to be satisfiable, that the clause is satisfied. One of these things must be true. a possibility is that Z is true, but X1, X2, X3 are false. This is a possibility. Because all I know is that the instance can be satisfied. The clause can be satisfied because one of these things become true. At least one of these things become true. It's sufficient that Z, the new variable, is true, but everything else is false. Does this make sense?
So in the first reduction, this cannot be the case, right?
In the first reduction,
that is true.
This can be the case, but the thing is X1 is true. Like you said, the final one to be true, right?
Yeah.
This X1 and X1, right? This is true. Then by default, this X1 must also be true. Like they are the same literal. You cannot assign true for X1 and not true for X1 at the same time. In the first reduction, right? If you say that this is true, then automatically this guy must be true as well.
Okay.
Does this kind of like make sense? I know it's a bit tricky to think about, but what I want to argue is that if you introduce a new variable just like this, right, you don't have control over Z is. In fact, I'll say that even if you set it to X1, like what you propose, you still don't have control which one is set to true. All you know is that the for set instance is a yes instance, so one of them must be true. It just so happens that X1 happens twice, right? So if you set one of them to be true, you also get that, sorry, if for example, the solution that makes this a yes, that kind of like confirms that this is indeed a yes instance, maybe for some reason it sets X1 to be true, it means that X1, this other X1 must also be true. They're kind of like coupled together because they are exactly the same thing. But if you introduce a new variable, they are completely different, right? So they're independent. So Z can be true, but X1 can be false. So in this case, right? In this case, if Z is true, if this was a yes instance, because of that dummy variable, right? Because of that dummy variable, then this entire thing, because of the fact that this was false, right, is a no instance. So we get something like for set is a yes, but tree set is a no. Of course, in this example, like maybe I fear that the confusion is because in this exact example, both are yes instances. But I think I can construct examples where a yes instance in for set is a no instance in tree set. Is that confusing? Do you need me to repeat some parts?
No, I think I get it.
Okay, so but I will mention that you are in the right direction. In a sense, you want Z to be always false, so that you want the other things to be true, correct? You always, in a way, you want to force the variable Z to be always false. Okay, so this is actually close. This is actually very, very close to the reduction. Okay, so in a sense, we want the Z to be forced to be false, and everything else become true. So how do you force this new variable to be false? Or rather, like, you always want to force one of these things to be true. Okay. Do you want to try it first, or do you want me to like just review?
Some kind of negation.
Very close, very close. Yes, yes. Some kind of negation. Yes. You wanna like try completing?
But since Z is a literal, you can't say Z is this value in this clause. Or wait, can you? Like, can you say Z is the negation of X1, X2, X3?
Oh no, you can't do that.
This clause. Yeah.
You can't do that. Yeah, you can't do that. You can't do that.
Hey, yeah. I'm not too sure for this.
Okay. Do you want me to review?
Is this answer in your slides?
No, it's not.
Okay, then just review.
Okay, can. Okay, so it's very close. So given x1, x2, or x3, introduce a new variable z and introduce a new clause. So you do this and introduce a new clause where the final one is z negated.
What the hell?
Okay, do you see? Okay, you say what the hell, right? But this is a valid reduction because again, I'm preparing an input. I'm preparing a new input and again, it doesn't have to resemble anything like the original 3 set. All I need to do is to prepare an input for 4 set. But all I do is like this, I introduce a negated set. So before I go on, do you see why this is true? Like why this reduction works? I mean, 3 set to 4 set is pretty much trivial. It's the same argument as before, right? If one of this is true, then we can satisfy these things, right? But what about the other direction?
Because like, how to say, like, it's like 1, 2, 3, 1 truth table.
Yeah. I guess in a sense, it's the truth table, right? So how I will argue this is that, like, look at the value z. Look at what z gets assigned to, right? So for example, z is true, right? For example, we don't know what it is, but without loss of generality, assume it's true. So then look at clause where there is negative z, the z negated, right? This must be false, right? This must be false. So in that clause, one of x1 or x2 or x3 must be true. One of these things must be true. So in a sense, this is how we force this thing to be false so that one of these other things must be true. Take note, it doesn't really matter like what this clause is doing. We just focus on this thing. And the fact that this negated z is false, therefore one of these other things must be true so that the original one, the original 3 set input must be satisfied as well. Is this argument confusing?
No, it makes sense.
Makes sense. Okay, great. So one additional question for you. Okay, so here I just showed x1 or x2 or x3, right? So the idea is to introduce a new variable z. So think about it. Oh, you are okay. Yes, you're drawing the truth table in a sense there, right? In the chat. Yeah.
Yeah.
So I'm saying, okay.
So you always hold, I don't.
Yeah. So either one of these things must hold, right? Because whatever value z is set, there must be, because it always happens in pairs, one of the clauses must be set to false, right? It's only either one of the values. So if look at the one that is false, and then the other one must be true, because we said that it was a yes instance. Okay. So here's the next question for you, because this reduction is a bit too brief. So this variable z, right? Let's say I have 2 clauses. I have x1 or now I have x1 or x4 or x5, right? This is clause number 2. This is C1, this is C2, right? Do I reuse the same z? Does it matter that I reuse the same z, or do I have to introduce another new variable like z2 maybe, for example?
It doesn't matter, right? Because you have 2 of them.
Correct. It doesn't matter. Yes. So I just want you to take note of this because you know, like it's for completeness sake, right? Like it's a bit vague if I just describe it as z like this, because in some cases, in some reductions, it might matter that they are the same z or not. I'm not saying like if they exist, but like it might matter. So I just want to complete the proof by saying that for all the clauses, all you need to do is to introduce a single new variable, right? Regardless of how many clauses there are, then do this process for z and do the same thing. I think this is a pretty decent exercise, right? I think your solution for the duplicate literals made it easier than I thought it to be, in case you allow it to be duplicate inside the clause, sorry. But if you want everything to be distinct, this is the way to go.
Yeah.
Yeah. So with this, so you solve 3 set to 4 set. So so basically, like the context behind this additional question is like, I think one student was asking me about the satisfiability problems. Then I was telling him that he was saying, so is 4 set more difficult than 3 set? Intuitively, it's true, right? 4 set is more difficult than 3 set. So I said yes, but if you want to formally do it, you can come up with a reduction, because it means that 4 set is at least as hard as 3 set. But what is interesting is that both 3 set and 4 set are NP-complete, right? It means that there exists a reduction between each other, right? Or at least a chain of reductions. So that student was asking me, so can you come up with a reduction from 4 set to 3 set? Right? This is a bit mind-boggling, because in a sense, 4 set should be like a more difficult problem, right? But because they are all NP-complete, there actually exists a reduction from 4 set to 3 set.
You can probably expand them somehow, right? So like you rewrite it such that one 4 set clause can be composed of multiple 3 set clauses.
Yeah, exactly. That's the idea. So for example, x1 or x2 or x3 or x4, you decompose somehow into like something of
some Boolean algebra magic.
Yeah, probably, right? So yeah, so this is kind of like the correct direction to go for, right? But I guess the reduction that we got in the end doesn't really rely on Boolean algebra. You might have something that works. Yeah, you might have something that works, but it doesn't have to use Boolean algebra. Yeah. If you thought about like the Boolean algebra magic, sure, you can tell me and we see whether it works or not.
Okay.
Okay, but it is indeed the correct idea. So decompose it somehow. Or okay, it actually depends on what you mean by decompose. I think what you mean is to like describe this into something equivalent in terms of 3 set formula, right?
Yeah, into like CNF or whatever.
I see. Yeah. So doesn't have to do that. I think like I mean like it doesn't have to expand via Boolean algebra. Yeah, I think I'll keep it at that so I don't spoil too much. But if you're interested to discuss it, again, like feel free to PM me. I think what I will do is that I might compile this into a sheet, then like maybe upload it into my sharing folder. Okay. Because as much as I like to release to the cohort, but I think like I don't have time to prepare like the full argument and such. Yeah, but at least I can give proof sketches for these things. So I don't want to release like proof sketches only. I'll probably compile like past year assignment questions also for practice in case you like. Yeah. Oh, one very interesting thing. So in case it is not, I hope it is not info overload. 3 set is NP-complete, right? But have you ever thought about like why they start from 3? Why not talk about 2 set? Like is 2 set NP-complete? Something like that. As it turns out, 2 set is actually not NP-complete. 2 set has a polynomial time solution to it. Very interestingly. Okay.
Is it because it's a Boolean and it something because it's a Boolean which has only 2 values somehow?
I think 2 set polynomial time. 2 satisfiability can be solved in polynomial time. I think what they do is this thing called the horn clause, right? I forgot the exact algorithm, but the rough idea is that this A or B, right? There's an equivalent form that you write in terms of implications. So I forgot which one. So for example, A, if I say that A implies B, right? I say A implies B. I think this is equivalent to not A or B, or the other way around. I forgot which one. Okay, but this is equivalent to this. So what you do is that for every 2 set clauses, you convert it to something of in this form, implication. Then I think what they do is they form a directed graph or something, then solve from there.
Wow.
But the 2-set problem can be solved in polynomial time, but 3-set is NP-complete. So it's very interesting how you go from like just at one single constraint, then suddenly it becomes way more difficult than it needs to be.
It is too much. 3, 2, 3, 4.
Yeah, I think this is actually this 2-set viability thingy might be in Intro to AI. I think I have briefly seen it in Intro to AI. Resolution. Yeah. 3-set. Maybe I'll keep this because I mentioned it, so I might just mention it here. Yeah. So okay. So that's
Yeah.
what I said. Feel free to
Thank
talk
you
to
so
me
much.
if you like.
Oh, by the way, have you started the 3211 assignment?
Not really. I just started this. I just talked about it this morning.
It's a. I think I might have broken the assignment.
Oh shit.
Because I don't know why, but Thomas suddenly PM me asking for my solution.
Oh.
Yeah.
Let's see.
I think it's a bit against the spirit of the assignment. But it doesn't work for the bonus. So
Okay, I see. Let's see. That's interesting. Okay.
yeah, thanks so much. See you around.
No problem. See you around. Okay, nice. So yeah, this is the final tutorial recording. I hope if you have been watching my tutorial recordings, I hope you benefited. Okay, and if you have any questions, do feel free to just PM me, because the tutorials are mostly prepared by me. The slides were something that I created last semester. Actually, most of it was created last semester. So I kind of know it best, I guess. Okay, so thanks a lot for watching, and I hope you enjoyed 3230. And I know it was a difficult module, but I hope the recordings that if you're watching this via recording, it made it as bearable as much as it can get. Okay, so thanks a lot, and I'll stop the recording now. Okay, see you when I see you.